And those two parameters, A and B, tell us about the stretches, the vertical stretch and the horizontal stretch. They also tell us about reflections if there's a reflection. So the thing to remember about the vertical aspect of the stretching is that whatever A is essentially the vertical stretch factor. Okay, now I've got absolute value signs there around the A in that statement, but that just means if A is negative and we ask what's the vertical stretch factor, you don't put the negative in your statement. You just say if A is -5, the vertical stretch factor is 5. And what that means is that every point that's above the x-axis, if the vertical stretch factor is 5, every point above the x-axis will be 5 times further above the x-axis, and every point below the x-axis is going to be 5 times further below the x-axis. So the vertical stretches away from or towards the x-axis. I say towards because if the vertical stretch factor is 1/2, then every point above the x-axis will be 1/2 as far away. In other words, it's going to be closer to the x-axis, but it will still be above. And every point below the x-axis is still going to be below, but it will be half as far away as it was before. In other words, it's going to be closer. Avoid the temptation to say something like twice as close. We don't like to use that terminology. We would just like to say half as close. Where things get a little bit sticky is when you talk about the horizontal stretch factor. It's connected to B, but you have to take the reciprocal of the parameter B. So whatever number is in the equation, forget for a second about negatives. If B in the equation is 3, then the horizontal stretch factor is a third. Okay? And the B is the number that goes into the equation. The 1/3 is telling us what's happening on the graph. On the other hand, if B were all right, sorry about that. If B is a number less than 1, like 3/4, when you take the reciprocal of 3/4, you get 4/3, and 4/3 is a number bigger than 1. So the horizontal stretch factor would be 1.3 repeating. In other words, everything would be 1.3 times further away from the y-axis because it's a horizontal stretch. Things go this way or this way relative to the y-axis. And then, of course, if A is negative, there's a vertical reflection across the x-axis. And if B is negative, there's a horizontal reflection across the y-axis. So take a look at your work, please. Does anybody have any questions you'd like me to go over? Go ahead, Janessa.
Can you use question 1 in the booklet?
One in the booklet, certainly. One of the things... I'm okay. One of the things that you're going to realize as we get deeper into this unit is that it's possible to go from one graph or function to a new graph or function in a number of different ways. Okay, so what this is saying is we have 4 different stretches being described here. Number 1 is a vertical stretch by a factor of 3. 2 is a vertical stretch by a factor of a third. The third one is a horizontal stretch by a factor of 3, and then a horizontal stretch by a factor of a third. And we're talking about going from, let's take a look at the first part of this question, to produce, so you have to watch the language very carefully here. To produce the graph of f of x, what do we do to g of x? So what we're talking about here for question 1, or the first part of this question, for this, which I'm going to label as that. Okay, what we're talking about is g of x changing into f of x. Because we want to produce f of x, that's going to be the end result. So the question is, what can we do to g of x to get f of x? Well, if I look at these graphs vertically, g of x is taller than f of x. And if I want to stretch g of x vertically, I'm going to have to take g of x and crush it down. And what I can do is take some point, let's just take this point on the original function, which happens to be 12 away from the x-axis, and compare it to this corresponding point. If I were to, this is kind of important, if I were to stretch things vertically, we keep the same x-coordinate as we compare points, right? I can see that this x-coordinate is only 4. And that means I can take the red graph g of x and I can squish it down by a factor of 1/3. So 2 is a way to achieve what we're asked to do in this part 1 of this question. We can do that. On the other hand, if I focus my attention on the vertical aspect of these, so when I looked at, pardon me, horizontal, when I looked at the vertical, g of x was taller, right? But when I look at things horizontally, I can say g of x is narrower. And I want to now stretch things horizontally to make g of x fit onto f of x. We're still talking about a way, to do this, g of x to f of x. I'm going to choose a different point here, Janessa, because I guess I could choose this point. I guess it just fits, and then compare it to this point, which is where I want to land. And the point where I want to land on f of x is 3 times further away. Do you see that? So what I could do is I could stretch g of x horizontally by a factor of 3, and that is number 3. Are you seeing where this is going now? Okay. Now, what's going to happen, of course, is when we go in the opposite direction, the stretch factors are the opposite. I mean, if I want to go from f of x to g of x, and we talk about vertical first. The order of these numbers doesn't matter, okay? But if I talk about vertical first, how do I take f of x and turn it into g of x? Well, I want to achieve this, and I'm starting off with this. I need to take that start point, which is the black point, and stretch it vertically, this time by a factor of 3. And that is number 1 in our key. The reason why this question can be difficult is we're coping with a lot of things here, a lot of numbers here, f of x and g of x, but that's number 1. And I hope everybody sees the connection here, that if g of x is stretched vertically by 1/3 to get f of x has to be stretched vertically by 3 to get g of x. And then finally, how can we get g of x from f of x if we talk about horizontal? Well, this black point on the original function is 12 away from the y-axis. I want it to be only 4 away, so I have to compress it. I have to squish it in, which means the stretch factor is a number smaller than 1, and it's going to be 1/3. And a horizontal stretch by 1/3 is number 4. And again, Janessa and everybody, I mean, you can have 2, 3, 3, 2. That order doesn't matter, but you need the 2 and the 3 first, and the 1 and the 4 second. Is that okay? Okay. Lynette.
14.
14? Okay. So we have a function which is a quadratic function, and there's some information that you're expected to know, everybody, from Math 20-1 about this quadratic function. If this quadratic function, and I haven't even read the question yet, I honestly haven't. I'm just looking at it, and I'm going to tell you what is, to me, obvious and should be to all of you, certainly by the end of the next unit, with a function like this. The x-intercepts are -4 and 3. I mean, you should look at that and you should see immediately that the x-intercepts are -4 and 3. And the reason is, this is y, and I'm going through really an extended explanation of why the x-intercepts are what they are. But for an x-intercept, y is 0. And this on the right-hand side, everybody, is a product. This becomes important for the next unit. This is a product, and the only way you can multiply two things together and get them to be equal to 0 is if either one of them is 0. So this is why we end up in Math 20 saying x plus 4 can equal 0 to produce an x-intercept, or x minus 3 can equal 0. So that's why I've told you the x-intercepts are positive 3 and negative 4. And all that just happened immediately. I want to say in my head, I didn't do this in my head. I just get used to the fact that the numbers that make these factors 0 are x-intercepts. The other thing you need to know in order to answer this question from earlier grades or earlier math courses is a 0 is a value of x that makes the function 0. That's the definition of a 0. A 0 of a function is the value of x that makes the function 0. But those are the x-intercepts. And I mean, this happens in every unit and every type of function. The zeros of a function are the x-intercepts of the graph of the function. So the question becomes, without graphing, what are the zeros of this function? You should be able to look at the function y equals 4f of x and say that's a vertical stretch by a factor of 4. And then you should be able to say, regardless of what the x-intercepts are not affected by a vertical stretch. So the zeros of A are going to be negative 4 and 3. You should be able to say that for B, y equals f of negative x is a horizontal reflection. And a horizontal reflection is going to take every x coordinate and flip it. So if we had an x-intercept at negative 4 and at positive 3, they're going to flip, and the 3 will become negative 3, and the negative 4 will become positive 4. Does that make sense? Okay. If we take a look at C, so this is a horizontal reflection. So the x-coordinates of the x-intercept switch. And it's just a horizontal reflection, so we don't have to worry about y. If you take a look at C, C is a horizontal stretch by a factor of 2. Because B is 1/2, the stretch factor horizontally is 2. What does that mean? That means if I have an x-intercept that is at negative 4, 4 to the left of the y-axis, it's going to be 8 away from the y-axis after that stretch, so the x-intercept would be negative 4. And if my other x-intercept was positive 3, then it's 3 away on the right-hand side, and if I stretch that horizontally by a factor of 2, it's going to be twice as far away, which would be 6 away, which would mean the x-intercept would be 6. On the other hand, for D, that's a horizontal stretch by a factor of 1/2, which means, everybody, that every x-coordinate is going to be cut in half. That's literally what the stretch factor does. It multiplies by the coordinate. And if it's a horizontal stretch factor, it multiplies by the x-coordinate, which is what we're talking about here. So that x-intercept at negative 4 is now going to be at negative 2. And that x-intercept at positive 3 is now going to be at positive 3 over 2, or 1.5. Have I answered your question? Okay. You know, and you could certainly make it more complicated by throwing a negative in front of the 2, in which case things would reflect and then squish. Is that okay? Okay. Other questions? Yeah.
Can you do number 5 in the worksheet?
Sure. So we have a graph of a function. We are going to learn in Unit 2 that this is a special type of function. It's called a polynomial function. It has the same kinds of properties as a quadratic function. It's just that instead of being a degree 2, like quadratic has x squared, this would be a degree 4. And we'll learn about that in the next unit. But you can see that both of these arms go up, and there's an x-intercept at 3, an x-intercept at 0, an x-intercept at -5. There's also a y-intercept at 0 since it passes through the origin. We want the largest positive x-intercept of this function. So piggybacking along the question we just talked about, when we see that b is -8, which it is, b is the number that you multiply x by, that tells us two things. There's a horizontal reflection, and if that horizontal reflection were the only thing that happened, then what's going to occur to every point on the function is that. That's the mapping that's associated with the horizontal reflection. But we also see that there's the absolute value of b is 8, which means that there is a horizontal stretch. And if that were the only thing that were happening, and I'll be very clear here, the horizontal stretch is this. Right? It's a compressive stretch. Things get squished together as opposed to expansive where they get pulled apart. But either one is a stretch. If that was the only thing that was happening, then the mapping would be this. Right? Every x-coordinate would become 1/8 is great. But when we put these together, and I don't think I really need this anymore, when I put these together, what that means is that x comma y maps to 1 negative, well, it has to be x has to be multiplied by -1, and it also has to be multiplied by 1/8. And I kind of stumbled and hesitated there when I said what I said and wrote what I said, because I've told you that the mapping when b is involved, everyone, is this. I've said it's 1 over b without the absolute value signs, right? And if I follow that rule, then it's that, right? I hope it doesn't confuse anybody that I wrote the negative on the top. 1 over -8 is the same as -1/8. So the bottom line here is each of these x-intercepts is going to be multiplied by -1 over 8. And this is more of an algebraic approach, but if I take -5 times -1 over 8, that's going to give me a new x-intercept. If I take 0 and multiply by -1 over 8, that's going to give me a new x-intercept. Well, it'll be the same. If I take 3 and I multiply by -1 over 8, that's going to give me the new x-intercept. So what do I get here? I get positive 5 over 8, I get 0, and I get -3 over 8. Notice it's not perfect, but that 5 is kind of written on the top because it's the top of a fraction. I'm getting way off topic here, but I would really avoid when you multiply a whole number like 4 times 7/8 that you avoid this. Don't do that. It's going to become important when we do rational work with trigonometric expressions and other functions. Okay. You're asked for the largest positive x-intercept. There's only one that's positive, so whatever 5 over 8 is, which is 0.625, rounded to the nearest hundredth is your answer. I chose to explain that using an algebraic approach. You certainly didn't have to do all this and think of mapping. What you could have done is you could have simply said, these points are going to be reflected horizontally and stretched by a factor of 1/8. So the -5 is going to become positive 5, and then I'm going to multiply by 1/8. You could have reasoned it out that way. Is that okay?
Yep.
Other questions? Go ahead.
Can you do question 3 in the workbook?
Sure. So we have, it's a numerical response question that's almost like a multiple choice question, but you got lots of choices. You have lots of options. And you're told that we are going to transform the point P. The ordered pairs below represent possible transformations. That means possible results after we transform that point P on the function f of x. The transformed functions are, well, there's 4 different ones. Okay. So, in the last question that Jesse asked about, I explained it with mapping first, and then I just used kind of our knowledge of transformations. I'm going to reverse that this time and use our knowledge of transformations. It's going to kind of look like mapping because I don't have a graph to look at, but I'm going to visualize the grid in my head. We're starting off with the point 2, 8. That's the starting point. This negative in front of 2f of x means things are reflected vertically. That means the y coordinate gets flipped. So that 2, 8 is going to become temporarily 2, -8. I guess it is kind of mapping, but I'm just visualizing it up at 8 and it goes down to -8. The other thing that's going to happen is this 2 stretches things vertically by a factor of 2. So not only does that 8 become -8, but it also becomes -16, becomes twice as great. So this will be the point 2, -16, and you can certainly go to the list and find 2, -16 and put in 8 here. You understand how the question is keyed, like how we solve it, okay, and record our answer. On the other hand, f of -2x means we reflect things horizontally, and that means that that 2 is going to become -2. I'm going back to the original. And the 8 is not affected by a b parameter, but there's also a 2 in here which stretches things horizontally by a factor of 1/2, which means the x coordinate is going to, as well as flipping, be cut in half, and that's going to make it -1, 8. And you can find the point in the list. Positive 2f of x is very similar to -2f of x in that the y coordinate is going to double, but it will not be reflected. There's no reflection here, so all that's going to happen is it's going to become 2, 16. Does your last one say f of -2x? What does it say? Just f of 2x. Okay. I did some cutting and pasting and forgot to edit there, I guess. This is going to be very similar to the second one, except it's only a horizontal stretch by a factor of 1/2, but there's no reflection, which means that original x coordinate of 2 becomes 1, and the y coordinate doesn't change. Is that good? Okay. All right, let's move on. We're going to be looking today at combining all of these things. And it's a relatively short lesson, but it's got a couple of little wrinkles in it. And throughout the course, I always refer to them as bumps in the road or things you're going to stumble on. There's one thing in particular here that you really have to pay careful attention not to make what I would call a common mistake. Because when it comes to the unit exam, and you guys want to do well on exams, I know that. You want the mark. That's what's the overriding thing in your math class. There could be 4 or 5 times where if you make this mistake, it's going to hit you 4 or 5 times. You're going to take 4 or 5 punches. And if there are 4 or 5 questions, each worth about 5%, that can knock your mark down 20 or 25%. Like it can really add up. So when I get to that point, I will highlight it for you. We're going to describe the effects of a, b, h, and k on the graph of an original function y equals f of x when we transform it to y minus k equals a f of b bracket n x minus h n bracket n bracket. Now I gave you a formula sheet, right? Does anybody not have a formula sheet? Okay. So again, I'm going to show you the formula on your formula sheet. We talked a little bit about this on Friday, but I didn't want to delve into it too much because Friday we were only dealing with A and B. But I mentioned it is on your formula sheet, and oh, there it is, it opened in the exact same location. I said that, essentially if there's no h and there's no k, this formula becomes what we talked about on Friday, y equals a f of bx. The first thing I want you to note is that this formula, y equals a f of b bracket x minus h n bracket plus k, is the same as what's in your handout here at the top of the page, right? It's just that this is y minus k. Again, it appears as plus k on the other side of the equal sign on your formula sheet, and that's probably what we're going to use most, if not all of the time. You might wonder why I type it out this way then, and the reason is I want to make sure that you understand there's this, level of consistency here with what we're talking about in terms of substitutions. Y becomes y minus k, x becomes x minus h. And what this question is really saying is, what happens when you change f of x to this new function? That's the bottom line. And the short answer to that question is everything that we've learned happens, still happens. So whatever effect h had on a function, it still has on this transformation, even though there are other things going on. Anything k did, anything we were taught that k does, still does it to the function. Same with a and same with b. But there's a catch to this. Well, there are a number of catches. The order in which we apply the effects of these four parameters a, b, h, and k is set in stone. Okay? It has to be done in a particular way when we follow this template. The parameters a and b must be applied first. And there are a couple of ways for you to remember that. One is when you look at A, B, H, and K alphabetically, that is to say you put them in the order they appear in the alphabet, A and B come before H and K. The other thing you could do, I suppose, is look at this equation, this what I call a template, and just read it left to right. And when you read it left to right, you hit the A first, and then the B, and then you hit the H, and then you hit the K. I want to make sure that you understand something here, and as we get into examples, it will become obvious why this is the case for many of you. All I'm saying is you have to do A and B first. I'm not saying you have to do A before B. I'm not saying you have to do B before A. I'm saying the effects of A and B happen before any effects with H and K. And I'm not going to explain why that has to be the case right now. I might explain it a little bit later. There's a mathematical reason for it. But this is the template that we're going to use. So this is a relatively short lesson, but again, it's got a couple of wrinkles in it. We're given a function y equals f of x, and it's transformed into y plus 2 equals 2 f of 3 bracket x minus 4 n bracket n bracket. Write the mapping of the given points and also sketch it. The thing I want you to understand, first of all, is that may appear on an exam rather than saying y plus 2. It could appear as g of x plus 2. In other words, everybody, g of x is the new function. And I could probably rearrange that and write g of x equals 2f of bracket 3 bracket x minus 4 n bracket minus 2. And you might wonder why I keep saying bracket b bracket n bracket n bracket. It's important. Okay. So there's the function. I would like everybody to take a minute and write down the values of those four parameters. Write down what a is equal to, write down what b is equal to, h and k. And I don't think I did it, but I might have just done it. Sometimes I will say A, B, C, and D. And that's because when we get to trigonometry, we don't use h and k, we use c and d. It's the exact same thing. Okay? I think for the most part, filling in these blanks is pretty easy. A is, what we're doing here is we're comparing, I want to go back to here where I just have a little bit more room. We are comparing this to this. We're just comparing the template on our formula sheet to the function in the question. So a is 2, b is 3, h is 4, and k is negative 2. Are we in agreement with that? I mean, I'm asking for two reasons. Maybe I'm wrong, in which case we better not proceed. And more importantly, I'm asking you to think about it and do the math yourself. But it looks okay, I think. Right. So before we sketch this and talk about mapping and all that, let's just write down what happens here. This is a vertical stretch by a factor of 2, because a is 2. This is a horizontal stretch by a factor of a third. This is a shift of 4 units to the right, and this is a shift of 2 units down. And again, if this is a written response question, you're not lazy like that. And I'm calling myself lazy here, but we're just in teaching mode, right? Well, you're in learning mode, I'm in teaching mode. This is just my way to explain to you so that you can see it on paper what's happening here. So I'm asking us to do 2 steps here in our work. And are we in agreement with what those parameters are doing to the function? That if a is 2, there's a vertical stretch by a factor of 2. If b is 3, there's a horizontal stretch by a factor of a third. Again, when I draw the arrow tips pointing towards each other, that means it's squishing together. When I draw them away from each other, it means it's stretching apart. And h is positive 4, so it shifts to the right 4 units, and k is negative 2, it shifts down 2. So we're going to take these one at a time. If I start on the left and I take care of the stretches, stretching this vertically by a factor of 2 will land it here. We'll land it here. It will be twice as far away from the x-axis if I stretch it vertically by a factor of 2. But I don't want to plot that point yet because I want to put both stretches on there. So right now it is 4 away. I double that to get 8 away from the x-axis in terms of a vertical change. And now I'm going to look at the horizontal aspect. That point is horizontally measured to be 6 units away from the y-axis. If I stretch that horizontally by a third, it's only going to be 2 units away. So this point, after stretching it vertically by a factor of 2 and horizontally by a factor of a third, lands there. I want to just go back in time for a second and say, had we started here and stretched this horizontally by a third first, then it would land there. And if I double the vertical distance, it still lands in the same location. And that's why I've told you, I don't care if you do A before B or B before A. A and B just have to be done first. Now I'm going to move on. I'm going to move to this point. Well, I stretch that point vertically by a factor of 2, and it's not going to move. It's going to be invariant with regards to that stretch. Because it is neither above nor below the x-axis, it doesn't get further away from the x-axis. Now I need to stretch this horizontally by a factor of a third. Well, this point is 2 to the left of the y-axis, so I need to put it 1/3 as close. A third of 2 is 2/3. I mean, you could use a calculator there, I suppose. But 2/3 on the left side is going to put it about here. It will be at negative 2/3. This point, I'm doing the vertical first. The vertical stretch will double the vertical distance away from the x-axis. It will be here. And the horizontal stretch by a factor of a third will not move it because it's on the y-axis. So it's not going to get a third closer to the y-axis because it's already there. And by the way, we can certainly be connecting these. I don't know to how many of you this is obvious, but given that that shape of that graph to begin with is a symmetrical W, there's a left side and a right side that are identical, but they're opposite, you could probably just graph the other points right now. But I'm going to go through and move them. So if I start here, stretch this point on the original function vertically by a factor of 2, done, right? There's nothing to do. Stretch it horizontally by a third, it puts it at 2/3 because 2 times a third is 2/3, and I can connect them. And the final point, stretch that vertically by a factor of 2, puts it twice as far away vertically. Horizontally by a factor of a third is going to put it here. And we can connect it. And now my job, so that's not done. That's just done with A and B. Now my job is to move that whole thing 4 to the right and 2 down. But let me show you that you don't have to move every point 4 to the right and 2 down. Well, you do, but there's a shortcut around it. Okay? I'm simply going to take this point here, which is kind of the leading point of the W. I'm going to move it to the right 4 and down 2. 1, 2, 3, 4, and down 2. But something I think that you should know, when you take a shape and you translate it, it maintains the same shape. So I can draw all of the other points in relation to this point. I notice, for example, and I'm not talking about a translation here, when I talk about what I'm going to say, that this point in relation to this point, if I were to take this and just move it over 1 and a bit and then move it down 8, I would be where that point lands. And it's going to be there. I mean, I could certainly do this. I could certainly take this point here, right? And some of you, I can tell by the looks on your face, would much rather do this and move it over 1, 2, 3, 4, and down 2 to get there. Okay? We can connect them. You know, along the same lines here, I can see that this middle part of the W from this bottom left part of the W is over to the next X value and up 4. So it's going to end up being there. Again, if that doesn't do it for you, then take this point and move it 1, 2, 3, 4 to the right and 2 down. I think you're getting the point, though. If I were to take this point, which is here currently, and move it over 1, 2, 3, 4, and 2 down, it's going to be there. And if I were to take this point and move it 1, 2, 3, 4 to the right and 2 down, it's going to be there. And we're done. Now, there's some mapping that we have to talk about here, but we'll get to that. Any questions on getting the graph? And this is certainly something you could see on a written response on an exam. Probably not on my exam. I think it might just be a little too simple for a unit exam, but by the time you get to the diploma exam, it might be a 2-mark part of a written response. All right, now we're going to do the mapping. So what happens to negative 6 comma 4? Well, let's go back and let's look. Negative 6 comma 4 is here, and it ends up being here. So it maps to 2 comma 6. Is here, and it maps to 2 comma 6. Would you agree? The original point is at negative 6 comma 4, which is here, and it ends up in this location. Is there a way that we could have done this without plotting the point? Well, let's think about this for a second. What happened to x was x got multiplied by 1/3, correct? And what happened to y was that y got multiplied by 2. And we took care of that first. In fact, if you take this negative 6 and multiply it by 1/3, I'm just going to write some scrap work down here. If you take that negative 6 and multiply it by 1/3, you get negative 2. And if you multiply that 4 by 2, you get 8. Negative 2 comma 8 is where the point landed after the stretches. Okay. After that, what did we do? Well, we shifted it to the right 4, which means after we multiplied x by 1/3, we added 4. And after we multiplied y by 2, we subtracted 2 because it was shifted down 2. So let's see if this idea that I have going on here works for, say, this point at 6 comma 4, which was an original point. I'm going to put the 6 here for the x. I'm going to put the 4 here for the y. And what I'm going to get is 1/3 times 6 plus 4, comma, 2 times 4 minus 2. So what is 1/3 times 6 plus 4? 1/3 times 6 is 2. 2 plus 4 is 6, if my arithmetic is right. Two times 4 is 8. 8 minus 2 is 6. Apparently, this point right here ends up at 6 comma 6. Well, let's look at it. Here's the original point. Where does it end up? Jackpot, 6 comma 6. Once you understand the general mapping, and I'll make it even more general in a minute or two, you don't need to read the points. For example, negative 2 comma 0, well, I'm going to take 1/3 times negative 2 and add 4. I'm going to take 2 times 0 and subtract 2. So I'm putting the x coordinate in for x in my mapping statement, and I'm putting the y coordinate in for y. In case it's not abundantly clear, I'm taking this and putting it here, and I'm taking this and I'm putting it there. And what do I get? Well, I don't want to get sidetracked here and talk about fractions and have a lesson on fractions. You can use your calculator if you like. 1/3 times negative 2 plus 4 is 10/3. And I see a couple people nodding, so this is 10/3, comma, 2 times 0 is 0, minus 2 is negative 2. Does that negative 2 comma 0 land at 10/3 comma negative 2? Well, let's see. Here's the original point. I'll use black this time. It lands here. 10 over 3 is 3.3 repeating. And that has an x coordinate of 3.3 repeating, and it has a y coordinate of negative 2. I'm not going to worry about the other mapping. The purpose of this part of the question, I guess we can write it down. This is going to become, I just won't show my work. 0 times 1/3 is 0 plus 4 gives me 4. 2 times the y-coordinate of 2 is 4. 4 minus 2 is 2. I just want to double check that. Put a 0 here, I get 4. Put a 2 there, I get 4. If I put a 2 for the x in the next point, 1/3 times 2 plus 4 is 14/3. I need some confirmation on that. 14/3. I put 0 in here for y, and I get -2. That's a way that you could do the mapping. And be very clear here about something. I'm not showing you this as, oh, by the way, isn't this interesting? There are going to be problems down the road where you're not going to have a graph. And you won't even necessarily have coordinates. It might be an algebraic expression. And you have to understand the mapping. All right, let's take a look at, could we do it all in one shot? I think it's easier in one shot. And I don't know if you noticed, but when I was doing this over here, when I looked at the original graph, I made a mistake and I said, oh, that's the original point. Because I've got too many graphs here, it can be confusing. I think it's reasonable that you could say, follow me along here, I stretch it vertically by a factor of 2, I stretch it horizontally by a factor of 1/3, I move it 1, 2, 3, 4 to the right and 2 down, and I'm done with that point. And then just repeat the process. Vertically by a factor of 2, doesn't move. Horizontally by a factor of 1/3, moves there. 1, 2, 3, 4, 2 down. And just continue. I think it's easier that way. For me, it is. If I have multiple steps in work, I have to keep track of which step I'm on. Whereas if my mind is focused on a single point, I can do all those transformations to it. Now there's an issue here because if you do it all in one shot on a written response, you have to explain maybe more in detail what's going on. Okay. All right, let's take a look at the next example. Use the graph of y equals f of x to determine the equation of the transformed function. So ultimately, this is the original one, O for original. This is the transformed function. And the questions in example 2, everybody, I think are relatively simple. Because finding the values of h and k can be quite complicated. So we're starting off with very simple ones because we're going to have to find h and k from this somehow. And it's not that simple when it boils down to it. The first thing you're going to do is you're going to figure out what A and B are. So when I look at A is a vertical stretch factor. So all I'm going to look at is the height of the original graph and the height of the new graph. Has the height of the graph changed? I'm not talking about where it is. Has the height of that shape changed? Well, if I were to look at this distance here, that's the height. And I can count the squares. It's 2, 4, it's 6 units tall. If I were to go over here and look at this, it's 6 units tall. It has not been stretched vertically. If it were stretched vertically, it would either be more than 6 units or less than 6 units. Okay? So I know A is essentially 1, except it might not be. It is, but it might not be. Has this graph been reflected vertically? Is that shape oriented upside down compared to where it was before? It's the same. So that means definitely A is positive 1. Now I'm going to look at the horizontal aspect of things. Well, horizontally, this is how wide the thing is to begin with. Remember, this is the original one, and I'm thinking that is 8. So that is 8 units wide. But when I look at how wide it is here, it's only 4 units wide. Well, that tells me that there's a horizontal stretch by a factor of 1/2, and that tells me B is 2. B is the reciprocal of the horizontal stretch factor, except it might not be 2. Maybe it's -2. It isn't. It's +2. Is the left-right orientation of the new graph the same as the left-right orientation of the original? Yes. You can see that the flat portion of the graph is on the left-hand side. If B were negative, it would have been flipped at some point in time left to right, and that flat portion that's still on the left wouldn't still be on the left, it would be on the right. So that tells us for sure B is 2. And incidentally, since you're asked to determine the equation of the transformed function, the reason why we are doing all of this is because you need to have numbers to put in for A, B, H, and K. We know what A is. A is 1, B is 2. We need H and K. So how do we find H and K? This becomes a difficult thing for you to explain on a written response. So on a written response, you would put more than what I'm about to say. What you do is you pick a point on the original function, and you perform the stretches and reflections associated with A and B. I'm just picking that point. If I take that point, which has to become this point, doesn't it? In the end, it has to become this point that I've circled in black. And I stretch it vertically by a factor of 1, it's done. And I stretch it horizontally by a factor of 1/2, it lands here, doesn't it? That's where that key point that I started off with lands. I don't want it there, though. I want it at the origin. And I can see from this that I have to shift this over 1 and down 3 to land where I want it to land. So once again, if the stretches landed here, then I have to end up saying, well, you know what? I have to shift that 1 to the left, and I have to shift that 3 down in order to make it land where it should land. Now, how would you do that on a written response? What I would do is, I would say starting with, and I don't know that you need to write this down, 2, 3 on f of x, that's the point that I chose. I chose this point to start with. B stretches horizontally by a factor of 1/2, making the point 1, 3. And I'm getting tired of writing already. Okay. Then what you would do is you would, maybe even if you had a graph, you could show this. You would say that that key point needs to land at 0, 0, which means I need to take 1 away from x, which means I need to shift it 1 to the left, and I need to take 3 away from y, which means I shift it down 3. So h is -1 and k is -3. Okay. Let's finish the question now. Now that we know that A is 1 and B is 2 and H is -1 and K is -3, we can write the equation. And you certainly don't need to write the 1 for A. All right, just hang on a second though. What if you chose a different point? What if you chose this point, which has to land here? Well, I stretch it vertically by a factor of 1. It doesn't move. I stretch it horizontally by a factor of a half. It still doesn't move. Right? Do you see why it doesn't move for the horizontal stretch factor? Because it's on the y-axis. So how do I get that, which is currently here, to be where it needs to be? 1 to the left and 3 down. And I won't keep you in suspense. You can pick any point you want. You're always, if you do things right, going to end up concluding that it has to be 1 to the left and 3 down. All right, let's try one more. I would like everybody to take a look at the two graphs. Remember that this is the original one, and this is the new one, or the transformed function. And I would like you to identify the values of A and B. And by the way, you don't, I think it's good to measure the entire distance horizontally, but if you look at that plateau, that flat part of the graph, it's 4 long on each. If there was any kind of horizontal stretch, then those two distances would be different. Okay? But the bottom line is the whole width of this, I believe, is 8. Am I right in my counting? And the width of the new function is 8. There's been no horizontal stretch. The total height of this beast is 6, and I believe the total height afterwards is 6. The only thing is that left to right, this thing is backwards. So B has to be -1. There's been a horizontal reflection. Now we need to know H and K. I'm going to pick this point as a starting point. I hope that you understand that's a relatively smart point to choose because it's not going to be affected in this question by A and B. First of all, there's no vertical stretch. Secondly, if I take that point and I reflect it horizontally because of the -b, it's not going to move. So where does it have to land? It has to land here. I got to change this question for next time. I think this is also going to be 1 to the left and 3 down. And that's why I'm saying I should change it. I don't like having the same result. I want that point, which is currently here, I want it to be here, so 1 to the left and 3 down, which means H is -1 and K is -3. And the equation of the function is y equals A. Again, you don't need to write the 1. F of bracket B x minus -1, which would give you x plus 1 minus 3. Any questions with B? All right. So we have a function f of x equals root x. By the way, the reason, now that we have f of x equals root x as opposed to just some function which we're calling f of x, when we find the equation and write it using this template, we will then be able to be more specific and put a square root in there. Okay. As a warm-up here, if we want to find, well, there's the equation actually, but we want to find A, B, H, and K and describe what's going on, and then I think we're going to be asked to find the equation. Can you do me a favor and write in the values of A, B, H, and K? So we have, I think, 28 people in the class right now. 24 people got it wrong. And this is the mistake. There's no question that A is -4. And it's without a doubt that B is 3 and K is 8. But H is not 12. It's not 12. What is it? It's 4. Have we lost our minds here? People are looking at us going, what are you talking about? It's 4. The reason is your template is this. This is the mistake that you don't want to make. The template is this. And there's a subtle difference between how this argument of the function is written here and how it's written up there. The b is multiplied in the template by something in brackets. And that means that this original or this transform function, you need to factor that 3 out to see that it's actually 3 multiplied by x minus 4. And then plus 8. It has to line up perfectly with that template. So you're going to need to erase that 12 that most of you put and put 4, because you can see that h is 4. In fact, you can get burned if I go back and I look at this, and you have this question in your head of 1 left and 3 down. Correct? You've done that work. But in the choices in a multiple choice question, you have stuff like f of bracket x minus 1, f of, and then minus 3, f of negative x minus 1, f of negative x plus 1, f of x plus 1. I know that most people will be looking at choosing one of those two, because you're saying 1 to the left, and your brain is accustomed to saying plus 1 is 1 to the left. But if I multiply this in, it's this answer that's correct. And if I factor this negative 1 out, it gives me the right appearance. It can be very tricky. So, what is happening here is vertical reflection, vertical stretch by a factor of 4, and again, I'm just abbreviating things. Horizontal stretch by a factor of a third. And by the way, when I walk around the room like that and go, 24, if you got it wrong, I'm not pointing fingers at you and saying, ha. I'm pointing out that there's a problem here in how you conventionally think. And when you make that mistake and then the mistake is pointed out to you in math, you very often learn not to make it again. Okay? If I would have just said, oh, and we factor out the 3, half of your brains would be half asleep and you wouldn't really worry about why. You need to make that mistake yourself. And this, of course, is 4 units to the right and 8 units up. There's only 2 reasons why I'm giving you this example. One is to highlight that you need to factor that b out all of the time. And the second has to do with the second part of this question, which is what's the equation? Well, we have y equals negative 4 f of 3 bracket x minus 4 m bracket m bracket. Did I get it right? Okay. But the original function is root x. So the original function f of x is root x, which means the new function is negative 4. We're going to have the plus 8. This whole thing means the square root of 3 times x minus 4. Right? That f is the square root. So f of pi is the square root of pi. F of puppy is the square root of puppy. F of 3 times x minus 4 is the square root of 3 times x minus 4. There's nothing wrong with you multiplying that 3 back in if you wanted to. And it might even appear that way on a multiple choice question or a numerical response question. But I think it's fine to leave it like that. So watch out for that. And it's going to happen. You're going to be going over assignments with me, and I'll say any questions, people go this one, and I'll go, well, you got to factor that b out. You got to remember to do that. So you can see there's a textbook assignment and some multiple choice and numerical response questions. A few transformations review problems. Tomorrow we're going to get into what are called inverses of functions, so we're temporarily moving away from this. So if you want a little bit of extra practice with transformations, there they are. Okay. So get to work, please. You still have about 15 minutes, I think. Yeah, roughly 15 minutes to work on this stuff.